Is this one working? Okay. Okay. For a little, I don't know. Hmm? Since I'm here, yeah.
You work with Klaus Landsmann, but not for your PhD, right?
Yes, I was there on my master's, and then my PhD was in Warsaw. I was in Gdańsk and in Oxford, and now I'm here.
That's in Oxford.
Yeah.
Okay.
It's more than enough.
Yeah. Well, now you're in Vienna. It's also good.
Yes.
So not now. Enough places.
Yeah. Yeah, I think so.
All right, welcome everybody. It's great to have this sort of inaugural lecture by GLOWACKI. So Jan has started already in February here in my group. And Jan is, I would say, a mathematical physicist by training.
I apologize for that.
No, but Jan worked with Klaus Landsmann for his master's and then at several other stations, including Gdansk and Oxford. And what did I forget?
My PhD was in Warsaw.
In Warsaw, where he did your PhD, yeah, and now he's here in Vienna for a bit longer. And Jan is interested in quantum reference frames and its application to relativistic quantum mechanics, quantum field theory. And yeah, his talk is all about that. Yeah.
Yeah, thank you. It's really nice to be here, not as a visitor, but as part of IQOQI. So I'm just going to start. Here's the plan. I will first have one slide of an introduction, and then jump into the particular approach to quantum reference frames that I work on, which is called operational, just introducing the basics, and then present the recent work together with Samuel Fedida about how this framework can be understood in the context of special relativity. And then if time allows, I would like to also say, so this is the first 3 points are solid, and then as the further we go, the more conjectural the story is, but I still want to share it. So I think I have some understanding of how the special relativity story generalizes to general relativity, to frames on curved spacetimes, and then how gauge theory can be also included in this picture, if time allows. So how much time do I have actually? Like, okay, so I think yeah, okay. So let me know when you're hungry. So for me, the story really starts 4 years ago in Seine. So many of you, some of you are here, and yeah, I'm pretty sure you recognize some faces. I'm here on the left. I lost some hair since then. Leon is on the right. So I bring it up because this is really when I learned about the existence of quantum reference frames as a research field. I met many people who are now my friends and collaborators, some of them. I also learned about the existence of IQOQI. I didn't know about that before. And maybe most importantly for this talk, I met Leon Loveridge, who's here on the right, and was developing the framework before. So after Sena, I started reading things, and many of the authors are here in this room, different kind of stuff. And then, but it really clicked for me when I started reading Leon's work. And after a couple of years, we started working together, and a few years later, and a few affiliations later, we have this paper that sort of spells out the formalism in its fullness to some extent. So we define, well, what are quantum reference frames for us, what are relative states, and how to transform. And since then, my main focus in research was trying to understand this framework better and generalize it so that it can be useful for relativistic physics. Because in this work, it's just done very generically with a group. And this group can be whatever one can imagine. So in a sense, I'm applying the framework, but I'm also trying to push it further, as you will see. So yeah, I'll just start with really the basics. So I like to view this approach as based on some principles. All of them are subject to debate, and actually many of them I wish to overcome and relax at some point. But here is how it stands now, and in the paper I just mentioned. So relationality, well, there is like a zero principle that we describe things in terms of quantum mechanics. Relationality means for us that we will be concerned with pairs of quantum systems, so pairs of Hilbert spaces put together with a tensor product. There is an invariance principle, so we will assume there is this abstract group that can mean very different things, but in general this is just a group, it's a topological group, and it is represented unitarily on both these systems. Nothing too weird yet, and maybe the most basic principle is that we suppose that the operationally meaningful observables that are somehow compatible with the symmetry structures are going to be live in this space. So bounded operators that are invariant under the symmetry structures. This G here means that we're interested in invariant operators. We have two actions, we put them together, we have an action of the whole thing, and we are interested in the fixed points of this action. Okay? Yes. Yeah, so S is for the system and R is for the reference. Oh, so just not to write it twice, so I have a unitary action on the system and on the reference. Yeah. No, sorry. Okay. Okay. I will change this notation. I see you are not only one confused. Yes. Yeah. So the group is represented on all systems considered. So in relativity, this will be the Poincaré group. Like everything is subject to some symmetry structure. And then another ingredient is this, what we call the frame observable. So the reference of the system on the right is supposed to serve, well, as a reference frame. And what we mean by that is something very specific, is that it is equipped with an observable, so it's a POVM in a very general sense, because we do need this generality to speak about orientation. So it's a POVM based on the space. This F is just, well, again, a topological space. But the key thing here is this action. So on F, we have action of the same group. So it's a G set, you could say, like it's a group acting on a set, and this set is a sample space for an observable. To be understood as a way, intrinsic to quantum mechanics, of speaking about orientation of a quantum system. So we will assume that, well, covariance, it's called covariance, it's a property of this observable that says that, so we have, observable is a map, like it takes the Borel subsets of this set F, set of frames, if you want, to operators on the Hilbert space. And we have G, the group G, acting on both sides. So we will assume that these actions are compatible with one another. So it doesn't matter if I act on a subset first and then extract the corresponding effect, or I take the effect of W and then act with my unitary representation on it. This is called covariance. And well, so this is basically this is it, almost. But this is super abstract. So to make it a little bit maybe more familiar to some of you, at least, is an example of such a frame observable can arise when we consider coherent state systems that, as far as I understand, are present in all of the QRF approaches. So a coherent state system is really, well, you pick a seed state, so just a pure state in your Hilbert space, and then you act with the group on it to give rise to different states, and this gives you the collection of coherent states. Coherent states, we usually assume that this collection is somehow dense in a Hilbert space, which can be understood as this equation. And then if we have something like this on our disposal, we can define a covariant observable by such a procedure. So in a sense, what we do is more general, but in other senses, it's less general, because this construction only works for coherent state systems that are described, that arise as I described, and people do consider more general coherent state systems, for which this construction doesn't take place. Is this relatively clear? Okay, cool. So there is two more things in this approach. First is the relativization map. So the symbol is yen, and it is a map that allows to construct observables of physical relevance, so invariant on the composite system, from observables on the system alone. So normally in quantum mechanics, we will be considered with bounded operators on the system Hilbert space. But now what we're saying that actually what we should be thinking about are invariant operators on both. And it turns out that there's a construction that somehow can allows us to encode any observable as an invariant one on the composite system. It can be written like this. So there's a couple of subtleties, and actually the further we go, the more subtleties are gonna arise. But well, that's just how it is. It's not completely trivial. So before I told you that this POVM is defined on the space. The space is here, sigma. So not necessarily on the group. It's a space on which the group acts. But here, well, for now, the relativization map is only defined for some cases, not for general G sets. And for this talk, at least up to half of it, we will only be concerned with this sample space being actually the group. So there is a subtle difference between a torsor, so a set on which group acts transitively and freely, and the group itself. And the difference is that the group has a distinguished element, the identity, while the torsor does not. But to write down this formula, I actually need to integrate over the group, because I have group action here. But what happens is that, well, I can identify my torsor with a group by just picking an element and saying, okay, this is my identity. And then I have provided a homomorphism, if you want, between these two spaces. And then I can integrate over G itself. And it turns out that the choice of this identity does not matter for this formula. So actually, it's all good, even though it could have not been. And this is actually going to be important. That's why I talk about this. And then there's another map that, given that sort of goes the other way around. If I have a description of a pair of system, but I fix a state of one of them, here the reference, I restrict my description to just the system alone. And this map is defined by extending this simple procedure. So imagine you have just a tensor product of two operators and a state. So you apply a state on the reference to the operator on the reference, and then multiply. So this is a number, and multiply the AS operator by this number. Well, it's no magic happens. Yeah. Yes. No. No, it's a bounded operator. So we think about observables as POVMs, really. So they have values in effects. So and effects are Hermitian and bounded, so you could do everything that's, we would say, operationally relevant by just considering the spaces of effects instead of bounded operators. But the extension is very simple, it's just linearity. Yes. Yes. Like what? Which one? I'm not sure where you want to go with this. So this map is defined for any bounded operator. So as long as your Krauss operators. Yeah. So I'm. So I'm gonna get to this. So if by the end of this slide you still don't know how I think about it, then ask again. Okay. Because now what we do is we compose these maps. Okay. So we take an observable on the system, we relativize it, so now it's invariant and defined on a composite system. But then we fix a state of the reference, this omega, and we end up in the system again. And this has an interpretation. This is how it looks like. So you see, we are rotating the observable that comes in accordingly, there should be a Hermitian conjugate on the right, accordingly to the probability distribution of the frame orientation, which is this thing. Yeah, this thing. So how we think about it is that, well, these frames, they're not part of the description in ordinary quantum mechanics, but yet, there's reasons to believe that they're somehow there, because we always need some reference to define our observables. That's exactly what happens here. And then the systems that we use to do this are ultimately quantum. But this thing is not apparent in the framework, in our understanding, for the following reason. So we are using these frames that are quantum systems, but are prepared in states that give them very good localization properties. So this measure, okay, does everyone knows what this measure is? It's a Born probability measure. So I have a POVM, I plug in a state, and then I get a probability distribution. Sorry, I should have said that. So the idea is that in the real world, most of the time in our labs, the frames of reference that we are using, they are classical in this sense that they are the states in which they come to us, or they're prepared, they allow for very sharp localization. And then you can see that if this measure on the right is very sharply localized on identity of your group, then this map is not going to do anything to your operator. So this is what we call non-relational limit. And it's a very simple result, but it carries lots of weight, because otherwise, if we're putting forward something like this, then we need to say why, we can do quantum mechanics without it, because we can. So this is my understanding why. Esteban? Okay? Yeah, maybe we can talk. Okay. N is a natural number. So, okay, sorry. So, so yeah, I guess I said it in words, but you're very much right to ask. So this localization property is really like, it can only be achieved in a limit most of the times. So some frame observables have this property that you can construct a sequence of states that brings your probability distributions as close as you want to the delta distribution. It doesn't always have to be the case, but the ideal frames and many other frames have this property. So that we can actually do that, and our restricted relative description is actually equivalent to the non-relational one. It's a property of a POVM, of the observable, of the frame observable. Yes, although there is, you can speak about, it's called localizable POVMs, or the property they satisfy is called norm one property, and it's, all this group theory has nothing to do with this. Basically, a POVM is localizable if every effect has norm 1, unless it's 0. So if there are projections, this is all good, but there's more general POVMs that have this property, and then they admit this localizable sequences of states. No, generically they not. No. Okay. Yes. Yes, it depends on everything. The choice of actions and the POV. Mm-hmm. No, but I don't think I understand why you would think so. Maybe you can try again. Yeah. Uh, not how. I mean, to have this notion, you need an observable that tells you where your system is. And this is exactly when you have to pick one, and that's the and it's gotta be covariant, and this is what your frame does for you. Yeah, but that's what I'm saying. In the Hilbert space without any specified observables, there is no sense in which your system is here or there. Yeah. Ah. Oh, this map. Okay. So if the frame is ideal, this is actually an embedding of algebras. It's an embedding of algebras. Embedding. So it's multiplicative, and it just puts this algebra inside of the bigger one. It's counterintuitive, but it works. And if the frame is localizable, so have this localizability property, this map is injective. Otherwise, it's not. I didn't see this question here. Yes, yes. Sorry. Okay, I don't know what happened. Yes, of course. Yeah. No. No, no, it's a different. So I think the best way to think about it is a conditional expectation. You condition on this one on the state of one part of your system. Well, Krauss operators, they arise when you like as a decomposition of channels, right? So I don't understand how you want to make a number out of a Krauss operator here. Like you're still in the state. Then you'll get a number, right? It's gonna be an expectation value of your restricted relativized operator. Maybe we need a board for this because I'm a bit confused. Sorry. Okay, so this is a framework, and I think it has some advantages and disadvantages when compared to other frameworks. An advantage, I would say, is that it is firmly based in mathematics. It is grounded in the probabilistic content of quantum theory, in the sense that it is not based from the principle of superposition, but more from the fact that there is this convex structure in quantum theory. And we're speaking about maps that preserve this convex structure, which are POVMs and channels and things like that. And well, that's obviously a perspectival statement, but I find it easier to understand conceptually what's going on. And the downsides are, well, many. I guess it's abstract and therefore not as accessible maybe as it could be. I'm trying my best, but it's still mathematics. It is, well, so I said this as an advantages, but it could also be a disadvantage because this concern was raised not once, that somehow this framework feels like it's not quantum enough because we only deal with probability distributions in the end. I don't think I agree, but it's been repeatedly raised. So I feel that, you know, in some sense, if you just superpose things and try to impose the linearity structure of quantum mechanics to like push them beyond classicality, this feels like very much quantum, but the problem is that it's only as far as this can go if you want to keep it mathematically rigorous. And okay, well, it is limited in a sense. So, for example, if you compare it with how far, I'll just finish the sentence, how far you can go with the tools of perspective neutral framework, there's only like a very small subset of those that are available in this universe. Yes. Yeah. Mm, yes, I think, yeah, okay, so it's maybe a little subtle. I would say the core of it, I mean, it's not like one thing is wrong and the other is right, but the emphasis is elsewhere. Because as far as I understand, and actually this perspective has been useful in developing the framework, is that in what you described, well, your states are pure. And then you extend the notion that, you know, by linearity of your Hilbert space. Whereas for us, a state is really a density operator, and the structure of this space is very different. So this lives in a Hilbert space, and therefore it makes sense to extend by linearity, but this lives in a actually a real Banach space. And the states form a convex set inside here. So there is a very different mathematical structure that is that, you know, natural to consider in the context of when you start your thinking from mixed states already, than when you start from here. And obviously these states live here, and you can construct mixed states from pure, blah, blah. But I mean, it's not like it's really, this is more general than this, or this is more quantum than that. They're different, and they lead to different objects that are being constructed on top of them. This, I would say, is more compatible with and in this sense, it's more general with like a GPT kind of thinking, when you have a set of states that is an abstract convex subset of some vector space. So this is how it happens here. And this just doesn't happen in GPTs, right? Generically. Okay. What do you mean? Like when I restrict when? Yeah. I don't think so, although I'm not even sure if this makes sense as a question. I mean, I understand the intuition, but then I said nothing about states so far, and deliberately so, because we don't have enough time to discuss everything. We do speak about relative states, and there are classes of density operators and the different objects. They're not just vectors in a Hilbert space. And because states in this way of thinking, they're somehow secondary to the operators. And you can have states that are pure, obviously. They're going to be projections in this space. And you can just only ever consider pure states of your system. That's allowed. But it's difficult to say that the framework restricts as a whole to like pure state quantum mechanics. Yes. Okay, this question makes sense and is interesting, and I don't know, but I'll be interested to actually try to write down something and see.
But you agree that these two things are equivalent to quantum mechanics. It's just the language that you, I mean, superscript phases, for example, in block vector representation of qubits, and it's just the same. The statement of the superposition is just probabilities in geometry based things, nothing.
Yes, of course. This is quantum mechanics, like both these things. But yeah, yeah, yeah. But then we try to go beyond quantum mechanics, right? And then it depends. You make choices. Yeah. Mm. Mhm. Yeah. Yeah, exactly. Yeah. And yeah. Sure. Yeah. But then there's yeah. Yeah.
Again, questions about the operationality of what we covered before, because in relativization maps, what I would try to do if I wanted to describe a situation in which I want to measure like the system, and then whatever measurement I do will depend on the state of the reference, right? So I measure the reference first, and then with the result, then I check the system. Maybe this is automatic or whatever, but I don't see any notion of like a post-measure the state, or
Mm.
I mean, it's just for one experiment, really. I mean, you do one experiment one time, and then you forget about everything, because if you wanted to describe the whole thing, the reference frame, I guess it will get correlated with the system, right? I mean, so you cannot separate it and say, no, this is a state omega or whatever. So I don't understand what the physics of this thing.
Yeah, well, I mean, this is a fair point. We're on a journey to try to understand this. This is I see, and
Where does this come from? I mean, it's like I don't
ah,
understand why people start studying something that they don't know if it's physical or not. Does it come from God or something? I don't understand this one.
uh, so I think in this specific case, it came from what's now called information theoretic approach to quantum reference frames, where sorry, it's just difficult to go back. Where a very similar map was constructed, similar to this, and it didn't make sense in this context, in their context. So their understanding was that when we do this, so uh, they were assuming that the reference is in an invariant state, which we don't do because often there are no invariant states. But in their world, the understanding was that well, there is no shared reference, or it's not just not, you know, it doesn't give you any information about orientation of a system. And then this measure here is just a Haar measure. So you got, and then this thing becomes a twirl. So you're kind of losing any information about the orientation of your system, and then this has some consequences in terms of information transfer in some sense, blah, blah. But this is not how we think about it, but this is one way you could try to think about it.
Maybe just quickly to follow up on your question, because maybe interesting to see whether there's some operational background discussion that led to some of this, which goes back to Rob Speckens and others. For example, the question, if you have a laser, it emits a coherent state, should we describe it as a pure state? Then there were people discussing, arguing back and forth, like, no, it's like mixed state because you need a kind of phase reference to actually say what the phase of your state is. And then the final answer is, it's up to you how we describe it. Like in one of these pictures, it's this pure state, and the other one it would be the mixed state, no? And this kind of explains and dissolves this discussion. So there's something like that in the background that led to some of the framework, and this is more an extension of that, I think.
To some extent, yes. Maybe one more comment along these lines. So this, the way I see it, is really something like the zero step before you do quantum mechanics, which is done in this, restricted relativized operators. So this is really to make sense when there is a symmetry principle on top of your theory to make sense of your observables. That's how I think about it. But it's not operational in the sense that inside this framework I can point to things that can be measured. Well, we're just not there yet. So what needs to be done is the development of invariant relational quantum measurement theory that would then also allow you to couple systems together to each other and evolve together, so like in quantum measurement theory, and then derive predictions. Because here you see so the unitary action can also encode time evolution, because why not? It can be whatever you want. And then you see that this action is diagonal. How we call it? I mean, it's just a tensor product of two. So they don't interact in this sense. The system and the frame, they don't interact dynamically. So, and to derive information about your system, you need another system that is going to interact, and that's a measurement instrument, and it's a different thing than the frame. So we're just not there yet.
This is very important. I would like to so you distinguish still conceptually between reference frame, measurement apparatus, and system.
Yes.
Okay. And now I didn't understand. I understand that if you want to measure, that will be some interaction. This I understand.
Yeah.
Measurement apparatus. In more general case, both with reference frame and the system.
Mm-hmm.
But did you say or not now that you need also interaction between reference frame and the system?
No, I just pointed to the fact that the frame cannot be a measuring instrument because it does not interact with the system. Yeah. Yeah, I was confused about this before, and I may said or wrote other things, but this is my current understanding. Yeah.
So can I understand your remark about this approach being more probabilistic based on probabilities rather than coherences by saying that this d mu omega of G is some probability distribution in a fixed basis?
Basis? No.
In the basis of the G coherence space?
Uh, well, so they don't always. I mean, I don't think this is the best way to think about it, but it is true in some cases.
Is this the cause that you don't have basis as in the other?
I think, yeah.
Is
Well,
this the cause why you cannot expect the phases, the relative phases in superposition like other approaches to
ah,
Yes.
I think Esteban knows more about
I
this.
think this is indeed the case.
Yeah, because you're classically correlating kind of quality distribution over G, right, with your observable in a sense. So it's not. So to the point Rue asked me, yeah, that's a bit like if I use the distant stars as a reference frame, right? That's a different statement from like using a measurement device to measure something, right? So I think of those two conceptually separate things. And yet the fact that the stars are kind of uncorrelated have a good property of them as a reference. But people, I agree, when you talk, they kind of like conflate the two, which is yeah. But I think yeah, they're two separate things. Yeah, the kind of like distant stars, which is more a bit like what's happening here, right? Like fixing a prediction. Except that here you describe them like quantum mechanics.
You're measuring the star, right? I mean,
Oh yeah, I guess
you don't,
indirectly by yeah, okay, that's a good point.
So if I do a quantum experiment on the table and I describe my wave functions as functions of like I know variables, then the table doesn't take part in the experiment. But it is necessary for my description to make sense. Otherwise, when I just write down phi of x, I mean, what is this x?
shouldn't you then measure the relative distance between
Yeah, so that
so and then it would involve the interaction with the measurement apparatus if you want to measure the relative distance. So don't measure one system because you will never find out the relative distance. You have to measure both things and subtract them or make an angling measurement.
Yeah, you need interaction with both things, yeah.
Yeah.
Otherwise, yeah.
But could you be like if you're so say that there's a measurement apparatus, there's a particle, and then you're using the table as a frame, no? When you write down the system, when you write down the state, you're writing down the state of the positions
Well, so as I said, the measurement theory is not done yet. So I don't have answers, like satisfactory answers to these questions. This is you could say this is a kinematical setup. It's trying to make quantum theory make more sense in the context of symmetries, especially in special relativity, where I maybe will get at some point. On the right, so we act on. I mean, that's just convention.
I don't know whether it's a state or a measurement.
Huh?
I don't know whether A is a state or a
No,
measurement.
no, it's unobservable.
It's observable, so it's an emission.
So we,
What's an observable for you? Is this
so I mean, it's
it's an effect of the POM.
yes, ultimately.
AS.
Huh?
The AS has to be an effect of the POM.
It doesn't have to be because we extend the algebra, but yeah, it's most
No, but I think it's small is bound to be that one.
smallest.
I think there's not much you can plug in there except effects. Otherwise, I would be very surprised.
Why?
Because I cannot make mixtures of anything else except effects or states.
Well, there's no mixtures. This.
It's just not a physical thing of it. So AS should be, in my opinion, should be either an effect or another state.
Well, then you're mistaken.
Which one?
No, no, it's not a state. A is not a state. It's not how to think.
So then it can only be an effect, or can it be anything else?
No, it can be any bounded operator on a Hilbert space.
Yeah, mathematically, yes, but I mean, what is the meaning of a bounded operator in a Hilbert space?
Well, if it's self-adjoint, then it's unobservable. Otherwise, it's probably an effect. Well, I mean, still it needs to be self-adjoint.
Back to the decomposition. Yeah, observable means something you can measure.
Observable is a POVM. I mean, I'm not going to solve quantum mechanics for you today. I'm sorry.
Yeah, I know.
We ask because we are all confused.
No, these are perfect questions, and yeah,
Can I just
sure,
one question is that so you could say that there is a difference when you look at the reference.
yeah.
On the one hand, to say what it means to define what it means that the reference points in a certain direction, and on the other hand, to actually measure in which direction it's pointing.
Mm.
So as I've understood it here, this is defining this covariant POVM defines what it even means that the reference points in that direction. And the fact that you
Yeah.
have here POVMs is kind of saying, in principle, this could actually be measured, but you don't care right now. You just define what that means. And then the kind of still to be developed measurement theory
Mhm.
and ask, how do you actually measure it? And how do you do that when you measure it together with the system?
Right. No, very, very nice point. So this is, I think, the closest how I think about. So we want to be, if we want to be speaking about orientation of quantum systems, then there is only one thing you can do actually, if you want to make it operationally meaningful. And this is to define a POVM on whatever you want to measure. And then it's there as part of your framework. It doesn't mean it can be measured. And actually, given the principles of invariance, it shouldn't be measured because this POVM is covariant. So the effects are not invariant under the group action, and it's not relational in any sense. It's somehow part of the framework, but it's not unobservable in the most operational sense.
The operational sense will be to say, okay, we have this set of interactions, and this set of interactions that we can switch on and off are just simply things that relate what I'm doing here with the reference system, and then make a ratio theoret of it. That would be the logical way for me to do, because then everything would be operational, and that's pretty much how Roti did, right? I mean, I don't understand this thing of coming up with some formula and then trying to find out some meaning for the formula. I mean, I think so.
No, no, no. I started with principles, and the formula.
Sure, you can go on, you can call it principles, right? I
No,
mean,
no, but the
principles,
formula,
yes.
the formula can. I mean, it's not there. That's why I don't talk about it. But this formula can be derived from the principles in some cases. So if you know you're interested in operators that are invariant and that arise from a chosen observable of the frame. So you fixed how you define or how you think about orientation of your frame, and you want things to be invariant. Then you're forced to use this formula. Like every operator that is meaningful is of this form.
Which principle will be meaningful? So which principle restricts you to use just the classical correlations between the reference frame of the system?
I don't know what are classical color relations between reference frame and system.
Reference frame, and then depending on that, then you're doing something on purpose.
But that's not what happens.
I mean, I'm trying to push on this difference between
Yeah.
free reference frames in order to better understand. So we kind of agree that the reason that you don't see the phases is that you take representation there. The first basis represents the group after it's.
But I don't think that's true. I mean, there is no, the group is uncountable. It doesn't label vectors. I mean, this is really to be thought of as a probability distribution and nothing more. It just comes from quantum theory because this is the word we're working with.
I think I might be wrong here, but I think that we can take this formula, replace, like choose a POVM that's just a PDM, like in the ideal case,
Yeah.
and the observables you get are exactly the same. I don't think this is the reason that they can't read out the phase.
To become, no?
Yes.
It's not.
I mean, maybe we have
Yeah,
to find
the
a different.
phase in the reference frame is the one that you don't see, but in the system you do see.
Exactly.
You see everything. Yeah.
And Tosa's question is, why do you not see it in the system? And I think that's yet to come.
Choosing that omega the same thing as choosing a seed for a unit state system to describe the
Choosing what? Sorry?
omega.
No, it's a different thing. So if you fix the seed state, it gives you a POVM together with the action. But it doesn't tell you what state your frame is in. And in particular, if you're gonna do this again. If you're in this example, if you actually prepare your state in this, your frame in this state, it's not gonna give you anything that's gonna be localized on G. It just doesn't work. So this, generically, this coherent state system POVMs, they don't have this interpretation as we do. Like, yeah. So the state phi of G doesn't say your frame is localized at G.
So if you have some phases in omega, then this phase is relative in this.
I don't know what's a phase on omega.
Exactly. If you write omega in the pure states.
No, but the pure state is a class of vectors. I mean, there is no phases there. Relative to what?
Superposition of two states to the relative state.
But there's one state.
But like it's quantum mechanics. So
Yeah.
like it's quantum mechanics, right? There is a state here and there's another state. There's an omega to a pure state at some cap, and there's
Yeah.
another omega for another state, another cap.
Sure.
And then there's a third state, which is
Yeah.
one plus the other, the omega of that,
Yeah.
right? That's all. And like this omega, we can actually have a whole family of these states, which depend on the relative phase of the superposition.
Sure. And then I have many states, but I only use one.
And then the question that you're asking is whether you can distinguish these resulting states that only differ by the phase of.
Okay, so in this, maybe I understand the question now. So in this, formula, the only way that omega enters here is by this probability distribution. And you can have many different states that give you the same probability distribution evaluated when with respect to this chosen observable.
I guess my question is, if you write omega as a superposition of two pure states with a relative phase in between, then that measure depends on its relative phase.
And what would it mean for it to not depend? Like, how do you imagine this? Like, it would decompose into a sum or something like?
Referring to what we were talking about, classical correlation. Like in some sense, there is a quantum correlation. The similar phases that is, I think, is what we were worried about.
Yeah. Well, if I understand, then yes, it's gonna depend on the state, unless the POVM is such that somehow it doesn't matter, which can happen. But generically, yes. I mean, this POVM can be informationally complete. It could distinguish all states. There's no reason why not. Okay, of a system, of the frame. Okay, right.
Yeah, maybe like if you have two spaceships, let's say, one
Sure.
is behaving as Gaussian kind of, and then you shoot photons to the other spaceship and count the time it takes for it to come back, and then you use this as a measure of distance. You neglect maybe the kickback of the photon, but you're in a kind of Gaussian state, so you're not really fixed in space. Then I think the observable that would predict such measurements is something like that, something like what you have.
That's good.
Yeah, it's
Okay.
just to give some intuition.
Uh-huh.
Yeah.
Okay, that doesn't that yeah.
The reference frame is one spaceship, and
So you want to have a countable group and an ideal frame, and consider this.
The most simple things, ideal frame, yeah.
Uh,
And now
uh,
the question is whether this framework can distinguish the two situations in which just the reference frame, not the system, I understood. Yeah? Just the reference frame could be either in the classical mixture of the group relativity or in corresponding superposition when I take.
yes. So I think in general the answer is yes, because the POVM can be informationally complete. Whereas I think in your example, if you want to compare these two specific states, I think I would need to check, but I think they give the same probability distributions, and therefore they won't be distinguished in terms of restricted relative observables. However, these are not necessarily the only things you're concerned about, because you're not forced to restrict your system on your frame on a state. It's still a quantum system, so you can, yeah, but settled. Well, we can talk about this at some point. Yeah. Okay, I've been here at some point. Oh yeah, I wanted to mention this paper on the side of actually what we were discussing, so like comparing this with other things that are on the table, recently finished by Tom Gali and other people, and Esteban, yeah. So these people, they know more about comparisons probably than myself. Right, okay. I will probably only cover special relativity today, and I'm gonna go a little quick. So this is based on the paper that's now on arXiv together with Samuel Fedida. The paper is pretty long, and there's many things that I won't talk about, but basically the story is the same. So we apply this framework to the context where the group is the Poincaré, and we arrive at something that looks a lot like quantum field theory. So most of the paper is actually more about comparison with the Whiteman setup, where the fields are operator value distributions. But I figured out that it's actually much simpler to talk about the algebraic setup. And this is also something that I feel I understand better. So I'm going to start with a recap, like what is AQFT, because this is where we're going. Just the basics. So, well, it's a net of algebras, which means that we have M is a spacetime in general. For us now, it's going to be just a Minkowski spacetime. So we have some regions in the spacetime that we care about. They're like pre-compact usually or causally closed. There's a collection of regions that we care about, and then we assign to them algebras. And this is not the most general setup, but let's say they're just subalgebras of B of H, of a fixed operator algebra. So for any such region, we have an algebra. And these algebras are understood as being available in this region. And this is precisely something that we want to make more operational in this setup. And this assignment satisfies some axioms, so that's isotony. So if you have a smaller region, there's less observables you can have access to, pretty obvious. Covariance, so in the context of the Minkowski spacetime, we can act on these regions by Poincaré transformations, and then the algebras, we can also act on the algebras, so we assume the representation of the Poincaré group on our Hilbert space. So we can also act on these algebras, transfer them somewhere, and this is the covariance. So these things are compatible. If I'm interested in a subset that is moved somewhere, then this is the same as taking an algebra here and acting on the level of the Hilbert space. Very similar to what was there before. And then causality axiom. So if you have two subsets that are space-like separated, so there is no causal curves between them, then we assume that the local observables should commute. So that's the basics. And we are going to generate something very similar out of the framework. Huh? Very good question for a different talk. Okay, so where we start here. Imagine, just very abstractly, like when you start to learn about special relativity, you're forced to consider different frames. And you just draw them. Like, I mean, there's some rulers and some clocks. And then there may be some other set of rulers and a clock. And what Minkowski told us is that they are related by a Poincaré transformation. uniquely. Any such pair of frames can be transformed to one another there and back by a Lorentz or a Poincaré transformation in general. So there is a bijection between the set of frames, this F thing, and the Poincaré group, and we restrict to this orthochronous part because we want to actually think about these transformations as being something you can do to the system. So you don't like revert the arrow of time or something, you just take this and boost it somehow. And this is going to serve for us as the sample space for the frame observable. So a quantum system can be, if it's very localized, then it just acts as a one reference inertial frame, but it can be delocalized, and then things get more interesting. So in this case, well, if we want to describe a system, but now bearing in mind that whatever we do, we need to specify our reference, then the observable is going to depend on which frame of reference we are using. Everything is classical yet. Okay? And this is, I mean, it's not confronted. This is why we consider representations of Poincaré group in quantum field theory in the first place. It's pretty standard. And so this assignment of the actual observable given the frame should respect covariance. Again, just for coherence. And then we put this QRF setup on top of this. So we define our frame on this set of inertial frames. It's going to be covariant with respect to the Poincaré group. And we can do relativization in this setup. And we can do restricted relativization, arriving at these things. Okay, now I'm just applying this. ER, yes. Yeah. Huh? You know, we have to fix it to give you a frame. There's many frames. Once you fix it, you get these constructions. So because of the Cartesian product structure of the Poincaré group, so it's really just translations, topologically just translations and Lorentz transformations. And because we only care about this not as a group really, but as a torsor, when it comes to this set of frames, the structure of this thing is really something like this. So instead of writing the group of translations, I forget my identity, and then what I'm left with is the Minkowski vector space without the zero. So Minkowski spacetime, Minkowski manifold. And then this L here I write for the torsor of the Lorentz group. And just forgetting the structure that is actually not there. It is subtle, but it's kind of important when we want to generalize these things. And then because of that, so my POVM, if you remember, is based on this product state and product space. And then we can take a marginal. So let's say I'm not interested actually in how my frame is rotated in the oriented in the same sense of Lorentz transformations, but I want to know where it is. And then I can construct this marginal observable. So I just put the full set here. Yeah, this is a standard procedure. And this I understand as a localization observable of my frame. So now there is an operationally meaningful sense to say, or like at least intrinsic to quantum theory sense in saying where in the Minkowski spacetime my frame is localized, given a state. And this observable is now Poincaré covariant. Before it was, sorry, this translation covariant. Before it was Poincaré covariant, but now we sort of, integrated over the Lorentz part, but we're still left with translation covariance, which makes sense. So yeah, and now if my frame is prepared in a state, this gives rise to a probability distribution of this marginal observable, which is now on spacetime, and this can have support that is not the whole thing. And this is how we understand the localization support of a frame. So instead of just defining a family of regions and declaring observables to be assigned to them somehow, like in IQFT, they will be somehow connected to this construction. If my frame is localized in this region, then it means that it gives me access to observable on the system bound to this region. Does it make some sense? There's less questions. That means that people are more confused, or okay. That's the picture. Maybe. Sorry. The tracing out is maybe not the best way. Like marginal. Yeah. So if f is this. Without knowing which. Yeah. No, no, but I think it's much simpler than what you're thinking about. So we have an observable that is, so the sample space is this thing, is the product, the Lorentz torsor and then the Minkowski spacetime. So if I have an observable that is based on this space, if I fix a state of the reference, I get the probability distribution over this set, right? Yeah, I fix a state. I fix a state. Yeah. Yeah. No, no. Before I give you a state, you cannot say anything. Yeah, that's right. Yeah. Yeah. And then if the state is somehow localized, then this support of this distribution is also localized, and then you can project it to M, and this is where your frame lives.
How do you know where your frame is if you don't have a frame?
What do you mean I don't have a frame?
Minkowski space, like there are no points, like you cannot say, oh, this is this point in Minkowski spacetime, right? Minkowski spacetime is, you need a frame to tell me where I am in Minkowski spacetime.
Well, that's exactly what's happening here.
No, you are telling me where the frame is, but I thought the frame is telling me where I am, where the system is, right?
No, there is no system yet, no? I mean, no, that's the thing. So the localization of the system is relative to the frame.
Yeah.
So if I have a frame that's here, then this is where I am describing my system, and my system does not have localization on its own. It's a quantum field, if you want.
If you have a frame as in orientation G, you also don't ask where is G, but you say, my system is in state H relative to that frame G, and you don't ask which frame is over the system.
Right, thanks. Okay, this is a beautiful picture, thanks to Samuel. I don't know how he typed this in LaTeX, but it's possible. Okay, so we go a little further. So yeah, this is not that complicated, really. I mean, as long as you accept sort of the starting point, which we struggle to accept, then you just apply it, really, and you arrive at this. So there's a single definition that, well, it's also by Samuel, by the way, that gives the whole thing. So we're going to define an assignment of local algebras that are defined relative to regions in a relational way. So it's dependent on the frame and the system. So how it works, I take a region I'm interested in, and then I consider a collection of all observables that arise by relativizing and restricting observables on the system, such that the support of the state of the reference is contained in U. So I take this collection. So these are all observables that I can ever think about accessing with the given frame that lie inside of U. And then I take the double commutant, which just generates an algebra out of it.
Quick question, Liz. So in the standard way, these local algebras for standard AQFT, they define the causal structure, right? So for example, this net of algebras tells you whether you can signal from one region to another or not. Now this seems to depend on your reference frame.
What do you mean? They put this condition on top of everything that they gotta commute if they're spatially separated, or you mean something else?
So it's part of the definition of what they mean by a net of local algebras.
Yes.
And so what follows from that in particular is the causal structure. What is a subregion of another region? Can you signal between these two regions?
No. This structure comes first. So the AQFT is built on top of space-time.
All I'm asking here now, what this net of algebras depends on your reference frame. Does it mean, for example,
Oh, okay, that's a very good question. Yeah, very good question. I'm just gonna get into this now. So this is a definition, and it does satisfy isotony. So you can just check this. You can check that covariance is satisfied as a consequence of covariance of the frame observable. The same thing, and just need to check that it goes through this completion to algebras. And what needs to be imposed on top of it is the causality condition. So it may happen if you just write this down for any frame. Maybe it will happen that the causality condition is not satisfied. But then maybe you've just chosen a frame that is not causal in some sense, and you want to restrict those frames that give you this. And so this is something we don't fully understand. We don't see any reason why this condition would fail. Like it seems that there are no-go results in quantum field theory that we clearly avoid. So we feel for now safe to just saying, well, we pick such a setup for which this holds because we want the theory to be causal. But there's other things that could happen. One thing is that, but this is a little complicated, so I decided not to talk about it, but if you ask me later, we can. So there is a condition you can impose on the frame alone that give you a version of causality for free. It's not exactly this, what we do normally in IQFT, but it is fairly close. And then you could say, okay, these frames are physical, they're causal, they're important. But another thing is that, well, actually, I mean, there's still quite surprisingly lots of research going on trying to understand this formula. Is this actually operationally meaningful to impose commutativity of all these observables? Well, and I think this has not been resolved, actually, at least not to my satisfaction, because this is supposed to be about signaling and not about simultaneous measurements. So we should be thinking, I think, about instruments and update rules in a very general sense to make sure that we cannot transfer information between these regions. And this is, as far as I know, this has not been done. So maybe there is actually a weaker condition that would be physically relevant. So I'm not too worried. I find this interesting to see what we can do with causality. Other things follow. Yes, I think if you want to have a relational AQFT, then you gotta impose this condition. And maybe not every frame is gonna give you this.
When you pick up a reference frame that very classical, you said, then you pick up, you go back. So I guess, I don't know, that one can also do that here. So from this relational algebraic to go into the conventional one, we're picking up reference frame. Now the question that Marcus posed could be now,
Well, then, yeah, sorry.
formal way, and that I believe you have framework with utility, namely that if you start with a causal algebraic causal regions,
Yeah.
which commutativity is satisfied, can you go into relational ones, which you construct, you have a way to construct, that it's not, commutativity is not satisfied, but once the reference frames become classical, you go back.
That's interesting. So you would like to start with AQFT and then apply these procedures to local algebras. So that's what people in York are doing, and they probably know. I think Leon with Fuster, they're working on something like this. And then what they get, as far as I understand, the paper is not there, but they get some sort of fuzziness of the borders of the regions. So normally you have U and it's there, but if you view it from a quantum reference frame, if it's not super sharply localized, then things get spread out a little bit. And I guess it is gonna, well, I guess it's gonna influence if the causality is only assumed on the AQFT level, then I would imagine it can break. But yeah, I think Leon is the better one to. Huh? What? Ah. Okay, we probably are hungry by now. Yeah, I just. Yeah, we can go for part 2. I'm just going to this slide. Yeah, I think we had a discussion already. Yeah, sure. November something.
Actually, are there any questions? Sorry. If not, I mean, yeah, we can also just talk to Jan afterwards and perhaps over lunch. So thank you again.